here's solutions to the review problems that I put up. So $200 per month into an account which earns 6% annual interest compounded monthly. And we want to know what happens after 10 years. Well, we really want to do this in terms of months. So let's convert everything to monthly interest. Monthly interest rate. That's going to be 0.5%. And of course, that's really equal to 0.005. Got to be careful with your zeros there. Okay. And so that's going to be our R. Alrighty. And we're doing it monthly, so we're going to have $200 plus $200 times 1.005 plus $200 times 1.005 squared plus, and that's going to keep going, and after 10 years I'm going to have, and let's see, now how many terms do I want? I want 120 total deposits. And the way I phrased it, the last deposit made earns no interest. So that's actually, the 200 I wrote there is actually the last one that went in because it hasn't earned any interest. This one is the deposit that went in and has earned a month's worth of interest. This one has earned 2 months, etc. And so to get 120 deposits, I have to go to 119. And there's that's that sort of annoying n plus 1 issue. So the very first one has earned interest 119 times, 119 months. And then the last one didn't earn any interest. If you switch that assumption in terms of the order, it would go to from 200 times 1.05 to 200 times 1.005 to the 120th. But I don't know. This is, I think, maybe a little cleaner. Okay, so that would be a huge pain to do without like a spreadsheet if we didn't have a shortcut. But we do have a shortcut. We know that we take that first term and we multiply it by 1 minus the ratio. Oh, you know what? Oh, my bad. Very important thing. This is a very easy source of confusion. This is the, let me just not use R here. That's the rate. That's the interest rate. But it's not equal to the, let's put that in math mode. It's not equal to the ratio. And people are getting confused about that. So we use R for two different things, unfortunately. It's really unfortunate. R for interest rate makes sense, but the ratio in this geometric series is not 0.005, because that would be if they only gave you the interest and didn't leave the $200. So if this was like 200 times 0.005, that means that first payment that you put in, they would give you all of $1 in your account instead of having the 200 times 1, which is the money you actually put in, plus the $1 interest. So very important that the two R's actually mean different things. Really, it's too bad, but we just don't have enough letters in the alphabet. Okay, so I'm sorry, I wasn't finished with this. That's to the 120. It's always the next power of the ratio, and then over just 1 minus 1.005. Okay, so I realize now that I don't think I was being careful about that in maybe some of the other videos. The distinction between the R of the interest rate and the R of the ratio for the geometric series. Okay, it's just always the number that gets multiplied to higher and higher powers is the thing that goes into these two slots. Okay, now that simplifies a little bit before we actually want the calculator to work on it. Let's just divide the 200 by, this is minus 0.05, and then it's times that same thing, 20th, and I'm just going to use that to switch it around. So that's 200 dividing by 0.05, actually that turns out to be multiplying by 200 again. So it turns out to be 40,000 times 1.005 to the 120th. You don't have to do this by hand, but it kind of cleans it up before you do it on the calculator. Okay, so let's look at what we're going to get. 32,000. So that's 32,776. And let's see if that's plausible. We put in 120 deposits of 200. That would be 24,000. And then we're getting a substantial amount more than that, but not a lot more. And that makes sense because a 6% annual interest over 10 years, it's not going to be dramatic. Remember, one nice thing is the rule. Remember, for checking these kinds of things, really useful thing is the rule of 70. And that is the doubling time for just a lump sum investment for 6% is roughly equal to, well, I'll just put equals, 70 over 6, which is about 11, very roughly. So about 11 years, if I had like the $24,000 just sitting there for 11 years, it would double. Well, I haven't had $24,000 in there for the whole time. I started out with just a measly 200 and then 400 and then 600. And so it makes sense that it's not even close to doubling the 24,000 investment. Okay. So some more money stuff. Retirement problem. I want to have enough money saved up in retirement so I can live off the interest, and that's a pretty good way to think about things. And I want $50,000 a year to live on at 5% interest. Okay, well that's probably what if you had trouble with this one, it's probably because you're overcomplicating it. You just want $50,000 to equal 5% of, let's say, A. I suggest A for that guy in the next one. That's it. Because that says if I have an amount A, the amount I will get each year to suck out of that is 0.05. There's nothing about powers or geometric here because we are taking exactly all of the interest away, and A is going to be left unchanged from year to year as long as I just take out exactly all the interest. Okay, and that's easy to solve. That's A is $1 million. Let's put commas in there so we can count the zeros better. So A is $1 million is what we'd like to get. Okay, so now this is more interesting. This is back to our master formula. If I deposit D each year, then at 5% annual, so now we're back to annually, measuring things in terms of years and not months, for 45 years, that's what I'm going to get with our master handy-dandy shortcut for the geometric sum. That's how much money I'm going to have at the end of that, and I'd like that to be $1 million. And so that's actually a pretty familiar problem. Just wanted to spin it a little bit. Okay, and so that's going to be, let's clean it up a little bit. Just like in the previous problem, we can sort of flip the signs around, and that's going to be equal to multiply the million by 0.05, which is 50,000. Oh, that's funny. That's that same number we had to start with. Interesting. 50,000 divided by D. Oh, actually no. So I still want the D over here because I want to solve for D. So I'm just moving things around a little bit, and so D equals 50,000 divided by this nice factor. So it's interesting that 50,000 reappears. Okay. And that's going to be 6261.7, which in fact, I think that's exactly the number we had for a previous problem, isn't it? Okay. Like 61. Yeah, I think this is the number I did in my example before. I thought I was changing the numbers, but maybe not. Okay, so that's how much we need to put in each year if we want to live enough to live on at $50,000. So that's interesting. Suppose $50,000 is our current salary. Then if I take that and I divide it by 50,000, what is that going to be? Okay, that's, I'll just put it in. It's about 1/8. Yeah, it's almost exactly 1/8 times 50,000. Okay, so it says that we should save 12.5% of our current salary every year, and then we should hopefully have saved up enough to live on our full salary just off the interest in retirement. Okay, interesting. That's a pretty big percentage, 12.5%. Not everybody saves that much, but it's a good ballpark actually. It's pretty accurate. Okay, so now what if he saves? Okay, so we're going to put in for Jim, we're going to put in that same amount D, 6261.70, but he's going to save only for 35 years and only at a 4% interest rate. Whoops. There we go. Well, how much of a difference does that make? Does 4 versus 5 make a big difference? Does 35 versus 45 make a big difference? Is he going to be pretty well off? Well, first let's figure out what his amount in retirement is going to be. So oops, I don't need that. Let's say A sub j. His amount that he ends up with after 35 years when he's ready to retire is going to be given by, I didn't put the 1 minus, there we go. It's given by this formula. We've got our starting amount from the geometric series, our master formula for the geometric series. Let's just calculate it out without trying to be clever. Okay. Okay, so that's going to be, and it likes scientific notation for that, but that's okay. Oop, lost it. That's going to be 461,190 about, and it's all approximate, doesn't matter. Okay, so about 461,190. Well, that's less than half of what we got, and shouldn't be too surprising for us. We know that delaying saving by 10 years is not a good thing to do, and 4% versus 5% might not seem like a big difference. You might think, oh, that's going to be about maybe 4/5 or 80% of what I started with. Well, it actually makes a bigger difference. So together, that's made a huge difference. And then what does that mean about the salary he's going to live on in retirement? Okay, now he's going to keep it in that 4% interest rate. Okay, so his sort of salary, it's not really a salary, I guess. Income, that's what I should call it. His income in retirement is going to be that amount of money he had times 4%. He's not likely to become less risk averse in retirement. People tend to get more risk averse when they get older, so it's likely he's going to keep it in that lower rate. Okay, and so that's going to be that 461,190. It might not like the comma times 0.04, and that's equal to 18,448. He's going to have to live on less than $18,500, whereas we're living on $50,000. So, and I do, by the way, have a brother-in-law named Jim, but he's a lot smarter than this about money. So he probably wouldn't be in this situation. But that's pretty dramatic. That's less than 40% of what I'm going to be able to live on, given delaying 10 years and is saving the same amount, but delaying by 10 years and going with 4% instead of 5%. Okie dokie.